Yale University, I'm working on some exoplanet atmospheric characterization, and this talk I feel will be a little bit broad in scope because I'm mainly interested in looking at planet atmospheres at a very global scale. And so the first topic question I want to talk about is, what do we know about exoplanetary atmospheres from photometry? So the reason I point out photometry in general is that there are two main ways to observe an atmosphere. We had a great introduction on transits and eclipses and phase curves, and so I'm going to be brief here. But so one way that you can try to learn something about an atmosphere is if you have a transit. So this, what's going on? I don't know if that's anyway. Oh, here we go. Okay, so if you're observing a planet during transit, this red ring is supposed to be like the atmosphere. It's a little exaggerated, but it could not be. And if you get absorption through that atmosphere, that's a transmission spectrum, you can possibly learn something about the composition of that atmosphere. And then if you're able to observe the planet through its whole orbit, you can see different phases of the planet, like the moon's phases, and the eclipse will show you the full phase of the planet, the day side, the side facing the star. And that will give you most of the information about the thermal emission of the planet itself. But you don't get to see the eclipse if the planet's orbit is edge-on. It's usually with the transit detections. So you see the decrement here. You see the portion of the planet's emission that's not being seen relative to the sun. And so this is kind of an example of what a phase curve looks like, a curve where you observe the planet in a photometric band through a whole orbit. So here's a transit and here's an eclipse. So I'm going to talk about phase photometry. I'm really interested in phase curves. Here are 3 space telescopes that have done great work in looking at phase curves and eclipses in general. Kepler, no, this wasn't Kepler's primary mission, but you can use this to phase curves, and that was in the visible. And then Hubble's Wide Field Camera 3 looked a little bit redder in the near infrared, but I'm going to talk about Spitzer bands, which are in a little bit redder than that, primarily because, well, these exoplanets, their own thermal emission is a little bit cooler than their host stars. So you're going to move a little bit towards the redder into the near infrared. So let's talk first about eclipses. Why? Because, well, there's more of them. It's easier to look at a planet during just the eclipse than for the whole orbit. So I'll be very brief about this. These are 2 plots from my recent paper. I'd like to focus on the right one, but to give context, this is a scatter plot of the eclipse depths, right? That represents the day-side thermal emission of the planet relative to its thermal expectation. So if the planet were radiating purely thermally at its equilibrium temperature, that would be 1 here, this dotted line. And so anything above this is super thermal. And so I'm going to focus on the redder points here, which just represent the Spitzer IRAC or infrared camera bands. So zooming in and showing a distribution of those fluxes relative to thermal, we have some interesting distribution. And so in the paper, I sort of quantify that this approach is something called the log normal distribution. If you remember from statistics, if you have an observable or measurable quantity that is composed of many independent processes that are all combining to create this measurement, then in the limit of many independent processes, you expect that sum to approach a Gaussian distribution with some mean and standard deviation. So in log space, or correspondingly if you have that be a product of many independent processes, you would expect to see a log normal distribution. So why did I bring this up? Well, it's suggesting that this distribution, looking at all these eclipses as a whole, is suggesting that there are many physical processes or maybe even instrumental processes that are creating this distribution. So it seems like there's a lot going on here, just looking at all the eclipse depths as a whole. And so if you have this observational data, what can you throw at it? Like, what's a good physically motivated way to reproduce these observations? Well, the most sophisticated way is to use a 3D climate model. So these were originally developed for Earth climate models, and I'm sure several of you, not many of you, have worked with these or seen these. And so I'll be pretty quick. They just, they're a 3D treatment of the atmospheric physics, and they also couple to the surface. So if you have oceans or if you have carbon cycle, all those sorts of things, you can take care of that. And most interesting to me is that you can capture the dynamics and the formation of things like clouds and the molecular absorption of species in the atmosphere. So it's really useful, and this is a really physically grounded approach and very sophisticated to try to model now exoplanet atmosphere. So a lot of work has been done to move these to exoplanets. And so one of the things that takes us away from the Earth-like regime is particularly the orbital geometries of these exoplanets, different stellar types, how big and how, in mass and radius of the planet that could change your surface gravity, and also atmospheric composition. And a lot of these planets that I'm going to be talking about that we have data on are hot Jupiters. So here I'm going to show some predictions from a very influential model from Showman et al. In 2009. So they used one of these 3D models to try to model a very well-studied hot Jupiter called 209458. And so here you're seeing the model curves in the Spitzer infrared bands, and I'm just highlighting here in the red is the 4.5 model-like curve. And you see that at that time, we weren't able to reproduce the eclipse depths. So we have a sophisticated technique, but we're missing something when we're trying to compare it to these data points, right? And so 5 years later, a paper by Zelm et al. Take a full phase light curve in 4.5. So now you have data over the whole orbit in this 4.5 band. And still, and here it's highlighting even more how the models disagree with the data. And so this is pointing to that while you can have all the physics in there and it's all well motivated, at this point it's not clear that that we can constrain those physical properties using the data that we have available. And so here you can see that the minimum here is over-predicted. And so what we were thinking is, well, we want to at least fit the broad properties of these light curves, right? So you want to fit, say, the amplitude of the light curve. You want to fit, so that would be also the eclipse depth. So you'd also want to fit where this minimum occurs. So if you remember, during transit, you've got the new phase of the planet, the night side. And so you expect maybe that the minimum temperature or the minimum flux would be during the night, the new phase, which is during transit. But if you see the minimum that's offset a little bit, that could tell you something about the circulation in the atmosphere, because that's telling you something is, like a wind is moving the cold spot away from that expectation. So that's one metric that you can fit. So these are all empirical properties of the light curve that you would like to fit to first order before you start moving on. And it's difficult, it's compounded by the fact that this is an example of what the Spitzer light curve, or Spitzer photometry starts out as. So this is the raw photometry. And so a Zhang et al. Paper from 2017, they outline a really good outline of how much work has gone into reduce Spitzer light curve data to get something that you can use, right? And even though there's been a lot of work to reduce the data and try to get at the real physical signal, there is, in many of these works, a lot of these experts are pointing out that there could still be very well be uncharacterized noise sources in the data. And so that's also hindering us. That could be one of, or several of the physical processes that are giving us that distribution of eclipse depths. So our approach, it's okay, I had a video, that's fine. So our approach is to start very simply. So we use the most simple physical model. And so as a grad student, this is nice for me because I can code up a model that takes 4 parameters. So we take a planet that rotates. We have a planet that heats up and cools down with some characteristic timescale. We have a planet that stays at some minimum temperature, and that could encompass anything that's not the stellar heating. And we have an albedo, so the planet has some reflectivity. Again, this is very, very basic. And we also, again, know the orbital geometry of some of these systems that we'd like to model, the stellar and the mass and the radius, and the temperature of the star, and then the instrumental band passes like Spitzer. And so we can model and generate a temperature map. We can model that with how you're viewing it to get through your light curves, and then you can try to optimize to find the best fit parameters of these 4. And so here's a non-animated version of what kind of the data products we get out. So this is representing the orbit of another well-studied hot Jupiter, 189733. And here just kind of showing you where we have orbit data. Here's the data in these black dots, and here's how we're fitting the data. So we can do multiple fits in different wavelengths. And we did this for a lot of planets. In fact, there are 13 planets that we looked at. Some of them are eccentric, and I'll get to why we like eccentric planets, or I like eccentric planets. And when we compare these models, at least at the first order level, we're doing a pretty good job. And so what this is suggesting is that there is a need at this point that even though Spitzer has done an amazing amount of work, it wasn't designed to do exoplanet atmospheric characterization. So we need to be aware of how we approach the data, especially when we're moving forward to James Webb. One thing I wanted to point out is that circular orbits, and this is motivating why I like eccentric orbits, they can have this, even with the 4-parameter model, you expect there's some difficulties. And one thing is that we have a timescale degeneracy. So I pointed out this phase offset. And so this phase offset, you can quantify how displaced that is. And that's represented in our model by a rotation period that captures any deviation from synchronicity or tidal locking, where the planet has one day side and one night side. So if you wiggle that away from that limit, then you can get effectively winds or capture that winds. And so this is kind of just a heat map of the likelihoods, and you can see that there's a large degeneracy between how much you wiggle that rotation period and what your heating timescale is. So those can kind of play off each other. And that's partially due to the symmetry of the orbit. You're always getting the same installation or a stellar heating. But eccentric planets could break the degeneracy. So here I'm showing a HAT P2b, which is an eccentric planet at eccentricity of 0.5, if you're interested. And these are really, really interesting because of the time variable heating from its host star. So you can see here at, it's almost, I think it's like a factor of 3 to 5 difference. I'll just kind of put this as a video. I had a video that's showing like it's kind of thing. It wiggles around. You can look it up. If you want, I can show you a link. But in summary, so this is the first part of my talk is that saying that photometry can capture these properties and tell us a lot about the atmosphere, but we really need to be careful about how we characterize our instrumental response. And so for the next couple of minutes, I want to talk about another project that's a little more theoretical, and I thought it would be a little more related to a lot of the astrobiology side of what's going on here. If we take this photometric approach, could we learn something about rotation on eccentric ocean planets? So I'm going to start with a very basic ocean planet model. An Earth-like planet on an orbit that is eccentric, but you can fix the total orbit average stellar heating to match that of Earth. And that's just characterized by this mean flux approximation. So all this is saying is that when you change the eccentricity, here's how you scale the orbit such that you preserve this value of F over F flux over the Earth flux. So just fix that to 1, tells you how to scale your orbit. So now we know how our orbit should be structured to preserve that amount of heating. And then we consider 2 rotation regimes. So one would be an Earth-like rotation, and one would be something that extends the idea of tidal locking to an eccentric case. Using the same tidal heating arguments, for eccentric planets, there's a pseudo-synchronous rate that remains pretty slow of order the orbital period until very high eccentricities. So we're going to call this the slow case. And so we can model these planets. We can look at the distribution of the ice and the ice cover and the open ocean cover and see what the surface temperatures are. And so I'm just kind of showing you that, you've probably seen some of these characteristic patterns of the eyeball where you see like a very concentrated melting point and then a more longitudinally symmetric point. And so I'm also just kind of pointing out to say that we did this, and pressure and temperature are some things that you can also measure in the atmosphere. And so what you might expect is that for the slow rotating planets, right around the point of closest approach, periastron, where there's the most heating, remember these are eccentric planets, that you would expect because the planets are more slowly rotating, they'll have more time to evaporate and give a greater column density of water in the atmosphere. So again, a very, very basic approach, but we want to see whether this could give a signature that could tell you in photometry whether you have a slow rotator or a fast rotator. And so what we did was we took James Webb bands and we simulated some light curves. So these are all in the mid-infrared from 5.6 micron to 25.5 micron. And so you're just seeing kind of the differences here. So one of these in the diamond endpoints is the slow rotator, and the plus signs are for Earth. And so I'm just pointing out here that in these bands, you can see that there's a characteristic difference. And interestingly, there might be something, so even in the broadband, there's an absorption feature of water in this second band here at 770 or 7.7 microns. So I was thinking, what if we took a color? So we took the ratio of 2 light curves. And so what I'm trying to point out here is that if you're able to observe in 2 bands and get kind of a color, a light curve color band, then you could see a pretty interesting difference, potentially, depending on where you observe. Even if you're not able to observe the whole light curve, this is one particular viewing geometry, but if you looked right at eclipse, you may be able to see a pretty big difference, and that color metric may be able to tell you whether you're looking at a slow rotating planet or a fast rotating planet. And with that, I think I will take questions. Thank you.
Do we have any questions?
So Arthur, when you showed HD 209458 at the beginning, citing Schumann 09,
right?
So you said you couldn't fit into the data. So that's the data from Nutsonnet 2008, right? When it showed an emission between 3.9 5,
Right.
people can understand,
Mhm.
need a lot of field.
Mm-hmm. Yeah, the ratio. Yeah.
Right, so was it because the data was so crazy over there? Like, were you able to fit it after the data was like fixed in 2014?
Right. So that's what I'm. So
Well, yeah.
yeah. So the idea is that even with the full phase curve,
Right.
we're not able to fit it. And again, if in this paper, Zell and the authors point out that they think that it's due to as you point out, a disagreement in the carbon chemistry, that there may be some disequilibrium chemistry in the methane and on the day and night side that you're not capturing or not capturing accurately with the model.
So I'm curious. So this might have been a weird, old data set from Knudsen et al. Sorry, this might have been some weird data set from Knudsen et al. But have you looked at any other hot Jupiters which actually has like a thermal inversion in emission feature and been able to fit it?
Right. So we have looked at planets where they have been modeled using inversion. I would say that our model itself does not at all it does not apply a thermal inversion model to try to capture the photometry. I would say that even with inversions in the atmosphere, there still remains a difficulty in capturing that inversion. There's still a difficulty to capture the whole shape of the light curves, even recently. So it may be very well. It seems very clear that there are inversion layers in planets, but whether you can take that and constrain the properties of that inversion within the context of the whole atmosphere in order to get the full picture with the light curve is another question. So.
Any other questions? Okay, thank you very much.
Sure.